We're going to wrap up our discussion of momentum with one last example. Let's consider one last type of collision. Here, I'm going to imagine that I'm going to shoot a bullet into a freestanding block of wood. That's my block of wood. And I, just made this quick in PowerPoint, so that's my bullet that's going to shoot out. I'm going to consider two situations. The first one is that the bullet actually sinks into the wood and gets embedded into it. Okay, so something like this, if you want to imagine it. All right. The second situation is I'm going to replace the bullet with a rubber version that's equal in mass, and we'll assume it was shot at the same velocity. This time, when it hits the wood, it's going to bounce off. Something like this. Now, the question I want to ask out of all of this is, in which situation did the bullet impart more force on the block of wood? So we need to ask ourselves an important question here. Can I use conservation of momentum? Well, what object are we really interested in? What motion are we really interested in? This question makes it seem like we're interested in the motion of the block of wood. So if this block of wood is my system, then the bullet is going to be external to that. So it's going to be imparting an external net force, which suggests that I can't use conservation of momentum. So am I stuck? Well, not really. A similar principle is still there. Let's just go back to that concept of change in momentum. So conservation of momentum said that the change in momentum was 0. But if we don't have conservation of momentum, then we just go ahead and calculate the change in momentum. So let's do that. So let's go through the situation 1 where the bullet embeds into the wood. We just need to figure out initial momentum and final momentum, and I'm assuming my mass isn't changing. So there was the situation, something like that. My initial momentum, I'm going to define as the moment right before it enters the wood. So it hasn't contacted the wood yet. Notice that initial momentum is going to be negative because I'm assuming it's going to the left, and we commonly say left is negative. And then I don't know exactly how fast it was going, but I'm not going to worry about that right now. So just assume this is some number. If it helps, think of, 50 meters per second. Okay, the final momentum is when it's actually embedded and stopped in the wood, so that final velocity would be 0. If I plug those into my relations up here, and then I'm going to simplify this down. So it simplifies down to just the mass of the bullet times the speed it had when it was first entering, just before it entered the wood. All right, now what I'm going to do with this is I'm going to go back to the momentum impulse relationship, and I'm going to rearrange it to solve for force. The question was which one applied more force, and so this is why I've rearranged it. Now I know what my change in momentum is. The t down here is contact time, remember, so this is some time that the wood was in contact with the bullet during the change in motion. I'm not going to worry about defining those, I'm just going to do it symbolically. So this is just some contact time, some speed, and some mass of a bullet. You might wonder what this is useful for, and right now it's not useful for anything, but I do want you to remember this ratio, mass velocity over time. Let's look at my second situation when I had a rubber bullet and it bounces off the wood. I'm going to go through the same process. The motion looked like that. I'm going to define my initial velocity as a moment just before it hit the wood. I'm going to assume that it had the same velocity as the previous situation, so I'll use the same symbol, and again it was going left, which is why I have a negative. But at this time though, I'm going to assume that the bullet had a perfect bounce off the wood so that it had the same speed it had before it hit the wood. Now, does that happen in real life? No, not necessarily, but just stick with me here. my point will be the same either way. The big difference is that now the direction is opposite, so it's going to the right. Strictly speaking, I can only do this when I'm looking at pure one dimension or horizontal motion, but so I wasn't drawing on top of each other, I gave a slight diagonal motion to it. That's not, you don't really need to worry about that right now. Okay, if I take these values and plug them in up here, I get this. Remember in the last situation, this was 0. Now it's changed. And notice that I have a negative velocity and I'm subtracting that quantity. So this negative sign and that negative sign are going to cancel each other out, and I'm going to end up adding those together. So I get 2 mb. I'll plug that into my momentum impulse relationship. I just need to plug it in right there. Now for this situation, I'm going to assume that the time of contact with between the bullet and the wood was about the same as the other situation. This is why I said that other situation was useful. Notice this was exactly what I had in the previous one. Now I have twice that. So this suggests that the bouncing off the wood actually gave me more force. And in general, that actually turns out to be true. So when an object is able to bounce off another object, it can actually deliver more force than if the two objects stick together. So if the bullet actually penetrates into the wood, it's giving it less force. Well, granted, yes, there's more damage to the wood if you want to think of it that way, but that wasn't the question. The question was force. So the rubber bullet would actually kick the block of wood backwards further than the bullet that actually went into the wood. So there's practical application for this. You've probably heard of law enforcement using rubber bullets as a non-lethal option. It would actually kick the person that got shot more than if it actually penetrated, and then there's certainly less chance for permanent injury that way. So as a final thought, here's an interesting consideration. If you're driving in your car and unfortunately you're going to run into a solid wall, it's actually better to do something like this, where you just completely crunch into that wall. In terms of the force that's applied to the car, there's less force in that situation than if you were to do this. Food for thought. And that's the end of our discussion of momentum and chapter 6 of our textbook.